Hello everyone, this is a video introducing the concept of the Common Task Framework for Science and Engineering Problems. This is an effort by the AI Institute and Dynamics Systems toward building out challenge data sets that we can be used by the community to test algorithms and codes. And a lot of the Common Task Framework will be based around both a set of example prototype type problems, and those I'll walk through in this video, as well as some leading challenge problems that we will recruit from the community to bring into a structure where people can test algorithms and look at how they do under really different and quite challenging circumstances and scenarios. So why do we want to have this Common Task Framework? The CTF goals are pretty simple. We're partnering with SageBionetworks. SageBionetworks is a nonprofit organization committed to promoting challenge data sets and open source software development around these challenges. And so for us, when we think about the CTF goals, there are various reasons why the AI Institute Dynamics Systems is promoting this. So first of all is we want to provide a platform for performance comparatives. So as we see in the community now, the development of machine learning and AI methods is widespread, using a diversity of techniques across a bunch of different application areas, but it's very difficult to understand how well they do relative to each other. So the idea here is to provide a platform for us to very easily see how well these different algorithms work in practice against each other under different kind of challenge scenarios. And in fact, that's exactly one of the things we want to start thinking about, is not only the evaluation and comparatives across data sets, but how well do they do across different challenge settings, whether it be limited data, high noise, low noise, parametric variability. These are the kind of things that we want to be able to stress test all of the methods being developed in order for the community at large to be able to evaluate how well these algorithms are actually doing in practice in the different settings. And for that, one of the goals here is that it becomes then a platform for the exchange of ideas and codes. And so what we have available to us now is GitHub repositories by the challengers themselves that we can actually download codes and start to work with those codes and improve upon. So for instance, maybe you find in your scenario you have limited data with high noise. You can look at the CTF and see which methods work exceptionally well in that regime or work better than most in that regime. And so then you could pull those codes, modify them for your purposes in your scientific and engineering application arena. And ultimately the big goal here is just to promote scientific and engineering discovery and really to accelerate the process for all of us in the community in terms of being able to achieve results much more quickly, because as a community we're coming together, sharing our code, but also testing it in these different environments under which become very important for us in the actual applications we're trying to solve. So that is the ultimate goal here, laid out. That is why we want to promote the CTF. And so what we've done now is set up the CTF in order to have both example codes that are prototypes that we're going to go through in this lecture, but then eventually have in people's challenging data sets where we really need to move the field forward, and we're going to recruit those into the CTF in order for all of us to both contribute and make progress in these very challenging scientific and engineering applications. So let's talk about the CTF challenges and the kind of things that we are stress testing the codes with. So first of all, what we want to do is we want to think about simple tasks like forecasting and reconstruction. Most of the data we're looking at is dynamic data, whether it's time series data, whether spatial, temporal, or from some dynamical systems. It is the AI Institute Dynamics Systems. So we think a lot about engineering systems where time plays a big role, and oftentimes the goal is to understand your data to set up control algorithms in order for you to sort of data-driven controllers. So obviously forecasting and reconstruction becomes a key task in all of what you are trying to do. Other challenges that really often create stress on the performance of your algorithms is how well does it do with noise. So noise robustness is a really big issue because oftentimes when we measure a system, we get noisy data measurements, and if you cannot actually handle that noise, then it's very challenging for your algorithm to be useful in that scenario. So we want to have algorithms that have noise robustness, or at least look at which algorithms are most robust to noise. We also want to take environments where we have limited data. So there are many instances in which we don't have a ton of data to build a model. We have a small burst of data, and from that you need to build a model immediately. What are the best methods for doing that? So for instance, in many applications where we do deep learning, it's typically assumed you have a great deal of data. And so it could be that in these limited data cases, this is not where deep neural networks succeed, and so what are your other options? And finally, another interesting issue for all of us is parametric variation. So what happens if you have a system where you have parametric changes? How well does your model adjust to the fact that you're in a new parameter regime where you do not have new data? And so how quickly can you build a model there in order to do these kind of tasks that are outlined here, which is, I want to move into a new regime and with very limited data get a very good model as quickly as possible, and I want it to be robust to noise, and I want to be able to do things like reconstruct and forecast what the underlying dynamics are. So that's really the layout of the challenges that we see before us, is that if we can set up a structure, and this is exactly how the challenge data set is set up, is that it's set up around trying to understand how well algorithms do under these challenge circumstances. The other thing right away that I want to emphasize here is that when you look at these challenges, we're going to get a multitude of scores. So oftentimes when you have a CTF, sometimes there's just some simple scoring system where you get a number or a couple numbers. Here, we're going to get a diversity of numbers, and it's very unlikely that one algorithm will be better than all others across all of these. But it could be, again, for your specific application, you can start looking. This is one of the really nice things about the CTF is you can look at different areas in your application and say, well, my application is really sitting right here in the limited data regime. What are the best algorithms that do well in terms of when I have very limited data? So depending upon your application area, you can go look here at the leaderboard in different areas for you to look at where you can start building models and which ones perform the best. Okay, so the example data sets that will sort of be the permanent collection that live on the SageBionetworks and for us to try different algorithms with are 3 dynamical systems applications and 3 spatial temporal models. And of course, these are often seen in the literature as the warm-up problems in methods papers. And so what we've done here is put all these method type problems directly into the CTF so that people can start just seeing how well their algorithm does comparatively across these different challenge application areas. So the 3 dynamical systems are going to be the Lorenz equations, we have the Rossler oscillator, and the double pendulum. So those are going to be 3 dynamical systems. This is of degree 3, three-dimensional system. Also 3-dimensional system is a 4-dimensional system. And so we will set up a set of tasks around this for predicting the future state of these systems. And of course, these are all chaotic systems. And so what we have to talk about is how we're going to evaluate a forecast, because short time forecasts, you should be accurate, but long time forecasts, you want to be have the right probability distribution, because you know that the sensitivity initial data are going to make it so you can't forecast well into the future, at least from a least square metric sense. For the spatial temporal systems, we have the Kuramoto-Shibashinsky equation, 2D Kolmogorov flow, and Lorenz 96, which is sort of a spatial temporal model. And so you have 3 spatial temporal systems, 3 dynamical systems, and those are what we have in order for you to try your algorithms on and see how well they work across these. The hope is that as you try methods, you can develop a method, see how well you do, see where your strengths are in the method, see where the weaknesses are, but also you have comparatives. And so now, instead of you having to sort of start doing your own comparatives across, well, what if you try these different techniques? Presumably they'll all be up on the leaderboard as well, and so you will immediately have a way to populate a table showing not only your performance, but how well it does compared to other methodologies. So those are going to be the challenges that we have as sort of the permanent collection on SageBionetworks. All right, so let's talk about what's next, which is what I wanted to do is I'm going to take one of these examples, which is going to be here, the Kermode-Shivashinsky model. And what I'm going to do right now is build a model for doing the different tasks. Accompanying this video in the link, it will be a link to a document, and that document contains the challenges and how we are actually evaluating the metrics for evaluating your performance. So I want to walk through this in the context of this Kermode-Shivashinsky model here. Okay, so let's start off. There's 4 different tests, and the 4 different tests are going to produce a total of 12 scores. Okay, and so what the goal is for you to download the training data set, and there in fact are a handful of NP arrays. That's how they're stored. And so you're going to download these NP arrays, and the tasks are well laid out in terms of what you're trying to use these with. The reason we have all these different NP arrays is each one of them is run in a different parametric regime, which you don't know where the Kermode-Shivashinsky is run. So that way, with it unknown to you, the idea is that you only have the data, and then from that data, you're going to try to do the following tests. So let's start off with test number 1, which is just a forecasting test. So what we're going to do with test number 1 is we're going to give you the data set. Here it is, X1 train NP array. Okay, so this is a NP array which has 1,000 time points, 1,024 spatial points. And so this is what it looks like here. And so this is the typical spatial temporal chaos of the KS equation. And so the goal of this next step is then to predict the future. I gave you the dynamics from time 0 to t with 1,000 time points. I want you to predict the next 1,000 time points. So this is the idea, is that you're going to produce now a matrix called X1 test NP array. Again, this is what you're going to upload. Is you're going to produce a set of NP arrays that you're going to put together in a tar package, and then you're going to upload to SageBionetworks, and that will automatically evaluate how well you did. Now, by the way, the reason I put a green box out here is let's talk about what it means to do a forecast, because when we forecast, it's very different to forecast far into the future, 1,000 steps into the future, versus your immediate next couple delta t's into the future. So what we've done here to evaluate the forecasting is we've broken this down into 2 different forecasting evaluations. The first is something like what you might consider a weather forecast, which is let's walk this out k steps into the future, and I'm going to evaluate from an L least square sense your model versus the truth. So what you're going to do is say, I need, for my score, the weather forecast score, it's the error is the short time error, is going to simply be a least square fit between your prediction and the actual truth. Now the truth data set, or is behind in SageBionetworks. Nobody has access to that, and so you're going to make a prediction for what that should be. It is evaluated, and that's your weather forecast score. The second score is the long-term score, which is when I walk many delta t's into the future, in this case 1,000 delta t's into the future. What we're actually going to compare is the power spectral density. So you're going to take the power spectral density, let's say averaged over the last k snapshots of this system, and you're going to compare the truth versus your prediction of what the power spectral density is. And that's like a climate forecast. What you're trying to get here is the right probability distribution far into the future. Again, because every system we're testing on has spatial temporal chaos, it is unreasonable to think about a least square fit model way into the future. And by the way, this picture here shows what maybe a power spectral density might be in the future at different time points. Okay, so this is what we're comparing. In fact, I think this is comparing the power spectral density of a model versus the actual truth. And then we're going to do a least square fit on the power spectral density. So that's how the evaluation happens, and 2 scores are produced. The 2 scores are E1 and E2. So E1 is the short time forecast, E2 is the long time forecast, and all of the scalings of the score go up to a max value of 100. if you have a perfect score, in other words, the difference between the short time is 0 here, or in the long time is 0, then your score is 100. Okay? And the baseline score, in other words, a 0 score, is if I just predict 0, then this is 1, then E1 and E2 are 0. So a score of 0 simply meant you guessed zeros as the solution. Your whole forecast is zeros, and if you get a perfect score, it's 100. Now, I'm going to say this right away, it's very easy to get negative scores. So the 0 guess is actually quite good because it almost looks like the average of what the Kuramoto-Shibashinsky spatial temporal field is doing. So anyway, don't be too discouraged if you get a negative score. That happens quite a bit as I've been playing around with different models. This is a very common thing. So your goal is to get as close to 100 as possible. Okay, so those are the metrics that we're going to use throughout. And so let's go ahead and start using this in actual code. So I'm going to actually write a code. I'm going to build a model. And the model I'm going to build is a dynamic mode decomposition model. And so this Jupyter notebook is also available. You can download it directly right next to the document that walks through this. There'll also be this Jupyter notebook that walks you through building a DMD model for the Kuramoto-Shibashinsky. So what we're going to do here is just do a Python code. It's very simple to execute. And all of this is based upon the new PyDMD package, which is actually quite an exceptional upgrade from the original PyDMD package. So if you're interested in playing around with it, this is going to show you how to do it. And it's really easy to use. And so it gives you a best fit linear dynamics model that, I'm just walking through this just to show how it works, but you can improve on it as you see fit. So the DMD model, we're first going to load in the training data set, X1 train. It's an MP array, and we're going to look at its shape. Here it is. And so now we have the data in there. Remember, this is data going from time 0 to 1,000. So 1,000 steps into the future with 1024 modes. Okay? And so now the goal will be for you to predict from time 1,000 to 2,000. Okay? 2,000 steps into the future. Now the DT here doesn't really matter. We've taken out whatever the actual DT was for solving this. We just think about it as you have 1,000 snapshots, predict the next 1,000 snapshots. Okay, so here's a code for doing this whole operation. This is the DMD model. You bring in here the DMD packages from PyDMD, so you can easily pip install PyDMD, and then this set of codes here brings in all the things that I'm going to actually use. And in fact, in this little code, the Jupyter notebook has more extensive use of plotting algorithms and so forth, but all you need to know about is this set of codes right here, which is you take your time. We just simply define 0 to 1,000 in steps of 1, and we're going to use what's called we're going to use optimized DMD with one time delay embedding. And the time delay embedding is really important, especially if you have standing wave structures inside of your data set itself. So this is the new example 1 out of the PyDMD package, and so I'm just using it here right out of the box essentially. So we're going to use this Hankel pre-processing. It's got one delay, and we're using optimized DMD. This is why we're calling it delay op DMD. You get to pick how many modes you want to use. Here you could use a statistical bagging for this. So it would be bagging optimized DMD here, but I'm just going to use standard optimized DMD. And I'm also going to constrain the eigenvalues. So the eigenvalues of the DMD model, I'm going to say that they only live on the imaginary axis and they come in complex conjugate pairs. And then fit the model. That's it. So I just define this and I fit the model to the data set X1. Okay, and that's going to do all the work for fitting the model itself. After the algorithm is done, then we're going to come here and look at the forecast I want to make. I want to forecast this from 1,000 to 2,000, and I just simply use the delay optDMD forecast module, and I just tell it what time I want. It produces the model. I call this for forecast, and now I have a forecast of this model, and I call this x1 test.mp. So this is an MP array. Once I have this MP array, that's what I'm going to send back and upload into SageBionetworks. SageBionetworks is going to take that MP array and it's going to evaluate both the short-term and long-time forecast and give back a score for this forecasting task that we have here. So that's the whole model. This runs in a matter of seconds, and so I can produce an output here. In fact, what you'll see here is I've taken this basic code structure. I've solved, if you look at the document, I've done all 4 tests with this same basic structure, and so that allows you the ability to evaluate how you're doing as you go. Okay, by the way, here's what the forecast looks like. This is the model for the forecast. So what I've done here for the DMD model, I've walked it out 1000 by 1024. So this is what my data set X1 test looks like that we're going to compare to the truth and get some kind of score. And the hope is, of course, I'm better than a 0. And let's see how close I get to a 100. All right. Let's move on to test 2. So that's the basic architecture. Test 2 is really going to be 2 training data sets with medium noise and high noise. So the goal here is to evaluate how well do you do in this modeling paradigm when you have significant moderates or significant amounts of noise to train with. So same idea here. I'm going to give you a training set. This is going to be X2 train, and X2 train is right here. And so X2 train, right, this is going to be a data set. Again, 1024 is the number of spatial points by 1000 time points. So you're walking this out in time. And if you notice here, I've put a bunch of noise on it. Okay, so this is X2 train. X3 train is even more noise, double the noise. So it really challenges you if you've got to figure out how to deal with all that noise. And it really puts pressure on the algorithms to also figure out how to deal with the noise. What we know is not all algorithms are the same in how they handle noise. Some will be highly non-robust to noise, and some will do quite well with seeing through noise. And so it's important in the scoring to understand which algorithms are going to do well with noise and which ones are not. It's very unclear in the literature when you read papers is how much noise did they actually put on to their system. Right? Typically what people do is show you their best result, and oftentimes they don't stress test it and tell you how well things do with limited data or lots of noise, but the goal here is that now we'll have very concrete metrics around this. So here's the goals with this. First goal is to take this training data set and first of all is just do a reconstruction. Can I denoise this? So this is going to be called X2 test is what you're going to produce is I'm going to just try to take off the noise and reconstruct what this data set was without the noise. Okay? And in fact, in that comparison, we're just going to give you a score, which is a reconstruction of a direct, what is your reconstruction of the data, what's it actually supposed to be, and that's going to be in a least square sense. We're also going to do a forecast on this. So now we're also going to take this and say from that noisy data, make a forecast, and in that forecast we're going to make this data matrix here called X3 test, and what we're going to do is look at how well you did from a probabilistic forecast. So this is going to give you an error metric called E3 here, and we're going to look at the long time forecast you can make with noise, which is E4, which is now we have 4 error metrics that we've produced just for doing the forecast in test 1 and now in test 2 and dealing with noise. How do we do this in practice? Same algorithm as before. We now just take here. The only difference here is that we put in X2 instead of X1, and then we simply do 2 pieces. One is we do a reconstruction over the range that we're interested in. So this is a reconstruction itself of what the data should be, and this is actually a forecast. So they're both fitting procedures. I have the DMD model, and I do the reconstruction task, and I do the fitting task, and notice what I have here. I've created X2 test and X3 test. Both of these are going to be uploaded into SageBionetworks to be evaluated. So that's your only goal, right, is to produce, I give you matrices with a goal, you produce matrices that are going to get uploaded and be evaluated. So the only thing that goes up to SageBionetworks is not your code, not this piece of code, although what we want to do is have a link to your code on a GitHub site so people can come look at that code. But what you're going to produce is a set of matrices that are going to get uploaded into Sage. It's going to very rapidly evaluate these and give a diversity of scores. So we repeat this with X3 train, by the way, and X3 train has double the noise of what we had in X2 train. So now this is a high noise limit, and it is very challenging to deal with that much noise. But again, it's really important for us. So the scores aren't going to necessarily be great here because it's very difficult to do forecasting and reconstruction with lots of noise. But our goal here is to see, let's see who can do well under these very high noise conditions, right? This is, if you're really solving a real problem, this is what you're going to have to deal with. And so we want to be able to evaluate this because it certainly pertains very closely to reality. Same kind of code base. This is exactly the same code. Again, this Jupyter notebook will be available along with the document walking through all the tests, along with the video here. Okay, so there we are. We upload those, and now we go to our test number 3. So we've tested just simple forecasting with clean data. We've now stress test the algorithms under medium and high noise, and now we're going to test it for limited data. So first of all, now what we're looking at is I'm not going to give you 1,000 time points. I'm going to give you 50 time points. So this is a very small stretch of time. And again, part of the goal here is to start understanding that it's not clear you can train a deep neural net to do this. What are the alternatives to be able to forecast this when I give you very little time, a very little time run here to do this? This is called X4 train. And so now your goal is the same as before. Produce a forecast for me. Like, tell me what the future of this is. In other words, walk this out, build a model, and walk it out 1,000 steps into the future, and let's see how well you did. Let's see how well this happens. So again, just like the noise case, it's much more challenging now because you have such limited data that walking it out into the future makes it very complex for you to, or even very challenging overall, right? But this is, again, this is the reality of what we often have to face, is that this is what we just have from our system. And again, for this test, we both have a short time forecast score and a long time forecast score. We do this not only in limited data with no noise, so we just say how well do you do limited data, but the next one is to then do it with noise. So here we go. Here's a DMD model again. This is just so simple. You just put in your data set, do the forecast. So the DMD model is super easy, right? Because I can just repeat this, and you'll see in the Jupyter notebook, I can do the whole challenge very quickly. I just load the data in, do a DMD model for all of it, and just see how well I do with that DMD model. And of course, there's things you can change in the DMD model, like the rank, like the time delay embeddings. There's a lot of different parameters that you can maybe play with to improve on what you're seeing here. But mostly what I wanted to do is at least provide one new notebook just showing how to walk through how to produce the data, and then allowing you to come up with your own methods and see how well they do. And hopefully the DMD would beat the 0 score, although that's hard to do with the chaos in general. All right, so you do this limited data run with noise now. And again, this becomes challenging in two respects, right? You have very limited data, and then you have a noise on it. So now you're putting these two challenges together, which in fact, maybe this is perhaps the most relevant in engineering practice to begin with, right? Is oftentimes you don't have a lot of data and you have noise on it. What are you going to do in terms of building models? The hope here is that what we're going to be able to see here in the CTF is some of the methods that are more successful in handling this specific case, which is very strongly related to reality in general. Okay, test number 4 that we want to do is to look at parametric variations in your data. How well can you build a model in one parameter regime and bring it over to another parameter regime, right? So how well do these models hold as you change some kind of underlying parameter in your system, which of course is highly relevant for physical systems. So for instance, maybe you build a model in a fluid flow system with Reynolds number 300. How well does that model hold at Reynolds number 600? These are the kind of challenges we face, because if we build a really great model and we have plenty of data, we want to see how portable it is into a new parameter regime. So the architecture of this is the training data set is going to be something like this. So maybe I'm going to give you some, let's say, 5 parameter regimes. And the way that parameter regimes are set up is that it's essentially you change one of the parameters, you ramp it up slowly over the 5 parameter regimes. And so I'm going to give you 3 training sets, and I'm going to give you two new regimes where we don't have this data actually. So the idea here is I'm not actually going to give you data here except for a small burn-in run, 50 time points. And so notice a couple things. So X9 train sits sort of in an interpolation regime in terms of parameter space, and X10 train sits in an extrapolation regime. So you're going to have 3 training data sets, 3 parameter regimes, and I'm going to predict 2 new parameter regimes. These are going to be the test sets. I do give you a burn-in, and then the question is, how well do you do? How well can you set up a model to learn how to very quickly adjust to parametric changes in order to have better performance? So that's kind of the goal of this challenge. It's highly relevant to so many models. This is sort of a generalization task, but oftentimes in the machine learning literature, people talk about generalization. These are both generalizations, but one is interpolatory, one's extrapolatory. And that's a really big difference between how well you're going to probably perform. Is when you're doing interpolation, it's much easier than doing a real extrapolation. And so in this case, we have both of these. Again here, there's going to be 2 new data sets produced, X8 test, X9 test, which is I'm going to predict the future here, and I'm going to predict the future there. And so we're up to now 9 test data sets, so 9 NP arrays that you're going to put together into a tarball and then upload it into SageBionetworks for it to actually evaluate on these different challenging scenarios. Now, let's talk about the evaluation metrics. You see here, what I've talked about is we have 4 test cases. So you have a number, in fact, let's look here. You have something like, you're going to have 10 training data sets, and you're going to produce 9 test sets. And the question is, and you're actually going to produce 12 different scores, or you're not going to produce it. This is what SageBionetworks is going to do, is when you upload your test sets or your approximations to the test set, what Sage will do is take those and do the evaluations. It'll look at short-term forecasts, long-term forecasts, these parametric variability, with noise, without noise, limited data. And what we're going to do is now, to do this, remember the top score is 100, it goes from 0 to 100. What we're going to do is produce some kind of spider chart like this, where you're going to see here on the spider chart, these are the scores from E1 to E12 around this wheel. And so the idea is roughly, right, we're going to look at sort of, so you're going to get a profile for your model. So for instance, I just did everything with a DMD model. And so in some sense, I'm going to get some kind of scoring chart, which is going to be reflective of how DMD does on these different scenarios. So we have here, and roughly the way I arranged it is like, we have forecasting and noise. So coming this way, remember the challenges, this is from E1 onwards. We're going to look at forecasting, then add in noise, then get into the limited data, and then finally look at parametric dependencies. So the idea here is for every algorithm, it will give some kind of profile score. So in other words, it's not like there's just one score. There could be an overall score that we might have, how well you did across all of these 12 metrics. But the idea here is to start thinking about enriching your view of what you might want to do. So for instance, if you're in a scenario where you have very limited data with noise, you might start looking right in this regime here, like who does well among this sector here, because that might be the application of interest for you. So we're hoping that the value of the CTF is not only to give a ranking or a leaderboard for every individual of these scores, but also sort of just a profile of how these algorithms do. It could be that some do exceptionally well in this sector, terrible in this sector, some will do well here, some will do others. It's very unlikely that one method will dominate across this entire spectrum of scoring, but if there is one, we should know about it, right? That's also an important part of the CTF itself. So that kind of ends this overview and also demo. Associated with this, like I said, there is a code to download, which has the Jupyter notebook I built for doing a DMD model for doing all the challenges, and you can look at that structure, and it's pretty simple, and so at least you have an explicit code to look at. And now hopefully also you understand clearly what we're trying to do in terms of not only what the challenge scenarios are, but what the goals are. And what we're hoping to do is build a very interesting ecosystem for people to share. And ultimately, this is an accelerator for all of us in science so that we can very quickly capitalize on all the work that's being done across the community and to start building those codes that are so successful into our own architectures for our own applications and advancing science and engineering disciplines that we're all actively engaged in. That's it. Thank you for your time.